Yeah, so I welcome you to one of our next research seminars, the TRR 391 on statistics for energy and transport. So here we have the research seminar today. We have a special guest, David Rügamer. He is a professor at the University of the AMU Munich. He is doing research in the field of data science statistics. And as also the title already suggests, he is working particularly on the intersection of, say, standard statistical model, as many of us do, and the direction of neural networks, deep learning, and these directions. He has a strong history in this field. So he is, in the past, he published a lot in standard, say, statistical journals, JASA, Biometrica, these kind of say statistical journals, and he shifted a bit his focus towards, say, more machine learning, deep learning aspects, but still his research is in this, I would say, intersection. And I'm very glad that he accepted the invitation and is here with us, and he will present us recent developments and progress in his current research. Thanks, and I think the floor is yours.
Thank you very much, Florian, for inviting me, and also thank you very much for the introduction. Today, so my name is David again. I'll talk about regression in the age of neural networks. It's a very broad title. I'll also start very high level, but then be more specific towards the middle and the end of the talk. As the title says, also, I will mainly tackle scalability problems in high dimensions. And maybe to start off with a motivation, something that maybe one or two of you have seen already, because I have given a talk about this also here in Dortmund a year ago. My recent research was mainly concerned, or to a larger portion concerned with semi-structured regression models. That's a regression model where you try to jointly train a statistical model, for example, to estimate the effect of patient data, the age, sex, treatment, and then also include things like the images of a patient maybe in your model to account for additional information that you have in the images. You do that by training one or multiple neural networks, and in order to jointly train them, you put everything into one large unifying neural network. You can make this happen by, you can define a convolutional neural network here, where you put in the image and then you learn some abstraction of the image here. And then what you define for the patient data is a very small neural network, actually a zero hidden layer neural network, which here are the inputs. So this would be, for example, age, this would be the treatment, and so on and so forth. And the edges of these neurons represent the weights. So essentially what you have here on the bottom is a linear combination of inputs times weights. The weights are represented by these edges. So this is a linear model. And then if you want to, learn the joint influence, you can additively combine them in an additive predictor, maybe transform this using an inverse link function to learn some parameter of interest, maybe the parameter of a density from a distributional assumption. And you can learn this by a maximum likelihood, because you can simply take the log density, sum all the contributions, and then essentially you're doing maximum likelihood by telling the neural network that it should be optimizing the log likelihood. Right, and so this is something that I have implemented with a couple of other people in the software package Deep Regression, which is on C-Run and GitHub. Normally, I would now go into details on how to use that, why it's already outdated, because we have to combine deep learning software and NAR. But the focus of today will be a bit different. I will actually, which is maybe surprising, focus on this part here, using fitting a structured model, a statistical model in a neural network. And that for itself is interesting, because there are certain properties that come with the training of such a small neural network that are interesting. Then this allows for quite some flexibility, second. And third, the main thing about today's talk is scalability. So fitting a regression model in a neural network does allow for better scaling. So you'll see a lot of these plots here. the x-axis is a number of parameters, a number of features, or number of observations. And then on the y-axis is typically on the log scale, something that like memory or time that where we want to scale have good scaling. So I'm sure you can all read these plots, but just to give you some visual clues, this would be good scaling, right? So this direction, this would be bad scaling. All right. So the scaling, how to scale models I'll present in 3 steps, or maybe only 2, and then give some outlook here. The first step will be to talk about some examples where we actually, in practice, were confronted with scaling probabilities, problems, not probabilities, and how a certain bag of tricks of using neural networks solved this problem. And then in the second part, I will talk about recommender systems, which might seem a bit contradicting the title that I'm talking about neural networks, but these recommender systems can also be implemented in neural networks. So we're in the same framework, and using these ideas here in the second part, allow you then to even scale better or more to larger data, to more interactions, for example. So that will be the main part, and then I'll talk about some challenges that we faced or we're going to be facing in using these neural regression models. All right, I'll start with the ideas from neural networks, and you just interrupt me whenever you have some questions. And start off with the examples, the promised ones. I have 2. One is a collaboration with Professor Stachel. He's a professor in behavioral psychology, and he is interested in. So there's these. There are 2 types of psychologists, I think. One are those that come up with the theory and then run the statistical tests and get the p-values and then publish in very high journals and maybe fake their data to get this to accomplish that. And then there are people like Clemens who actually do not have any a priori assumptions, but look into the data and try to find patterns. So in his case, he was involved in a large study where people have their smartphone activity was logged. You can see this maybe here also. There's a certain timestamp with what the person did, and now he's interested in, can I somehow explain the personality of a person based on their app usage, which in some sense makes sense, right? If you look onto, I don't know, like if you go to bed and you listen to a podcast, then you have a different personality than if you go on Twitter and rant about politicians, right? So this is like 2 different personalities. So that could make sense. The challenge here is that, one, we have these usage logs, which are for hundreds of people, hundreds of participants. We have over a span of months. We have logging data, and maybe you can see this here on a millisecond basis. But that's a lot of data that you cannot fit in any memory at once. You need like a database for that to store, and then you can only load batches of data into your model. That's one challenge. That's the large scale challenge. The other challenge is the app usage. There are thousands of apps that potentially can somehow tell something about your personality. And I can show you already some result. So we were trying to fit a varying coefficient model, so a relatively simple statistical model with where we have non-linear effects varying with the apps. And here are the number of app categories, and the more you increase the number of app categories, the more the time spent fitting, in this case, a big additive model. This was MGCV-R package. The time spent and the memory costs will increase. So this is the vast scaling from before. Means that even and there is special functions even for categorical or very coefficient models in this package. Even with special software, you scale exponentially if the number of categories increase. So, and we had not only 20, 40 or 60 categories, but it was 600 or something like this. So it's quite a challenge also to get simple models like this fitted in standard software. The second example is a collaboration with Dr. Leo. He's a biomechanical researcher, and he's usually, or in some cases, in many of his studies, he's interested in, so he puts sensors on people's body, and then tries to understand how the body moves. And you can measure things with sensors that measure easy measurable things that you could potentially measure with your smartphone, like, for example, the acceleration of your foot, the acceleration of your thigh, the acceleration of your trunk in certain dimensions, X, Y, Z, so front, side, up and down, or maybe use a gyroscope. These are things you can measure with your smartphone. And then there are things that you cannot measure with your smartphone, like, for example, here, the ground reaction forces or the moments. For that, you need some laboratory setup like here. And now the question is, can we maybe predict those signals here, which look like this here? So they are also function over time. And the time here is just from 0 to 100. So that's one step. If you take one step, then you will produce one of these functions. The question is now, can we predict these guys here, which are hard to measure only in a laboratory setup? Can we predict those with those guys in the background, which are potentially measurable by your smartphone? So that's the second setup. And why this is difficult, or why this is challenging, you see here, this is a recent paper with Alman Stöcker, who some of you might know. If you have a certain number of functional observations, if you have a certain number of functional predictors, so that would be gyroscope one direction, accelerometer in another direction, or time points, then again, the scaling is super linear. It increases more than linear if you increase those guys. And that was fitted with both an additive model software and a boosting software. The second one, I was even involved in writing the package. So I actually also know why this is scaling super linear. And yeah, this is another problem that we will tackle in the course of this talk. In particular, because in this study, we not only had 100 observations, functional observations, but 50,000. And we didn't have just 1, 2, or 4 predictors, but 64. And you see here that we're already in the 4 gigabytes here for some of these observations. So you can imagine that if we take like 50,000 of these observations and then 64 predictors, this probably will be quite expensive. All right, so what is the bag of tricks that you can apply, and how can you embed your statistical model in a neural network and then thereby make the scale for such data? For that, we'll start with the functional regression model, so the later application. So for those of you who are not familiar with functional regression model, a quick recap. So we have functions here, y for every observation I, so that's every participant. This is the time t, so the time during the step that you take over some interval. This is the outcome function that we want to predict. And these are input functions over potentially another time domain. And this is essentially a linear model. It's multiplying x times beta. But because we have as an output a function and as an input a function over time, our linear model is trying to estimate a coefficient surface in 2 time dimensions, beta, s, and t. So this guy here will be our linear influence. To make this a bit more clear, here's an example. So you have your input function here. You observe maybe discretized values here. Then we have, for example, a bump here. And then we look up, and this is our very sparse coefficient surface here, this center plot. We see that there's a negative effect. So multiplying a positive bump with a negative effect gives us a negative bump in the output signal, right? And similar, if you have, for example, look at A and B, those are positive effects. We have a positive signal here. So if you multiply this, we get a small positive bump here, and here a wider bump at the C time point. So this is how these linear models in function regression work. In practice, what you do to estimate this, because it has an integral, it has a coefficient surface, this is things that you cannot represent in a finite dimensional space in a computer, you approximate things. So first of all, as you saw here, you have discretized values. So we have R discretized values of our input signal, and then we approximate this integral using some approximation scheme, so some approximation weight, for example. That's how we can get rid of the integral. And this guy here was also a function that we need to somehow represent in the computer. For that, we can take a tensor spline approach, a tensor product spline approach. So we set up a basis function for the S direction, maybe a B-spline basis. We set up a basis function for the T direction, so maybe a B-spline. Make them chronicle them use a chronicle product, and then learn their coefficients in a parametric fashion. So this is how we represent the bivariate nonlinear function using a spline approach. And finally, we also observe these guys here on a discretized value, the t time points. So we have tq time points from q1 to capital Q. And so this is essentially then our final model. So if that was not, maybe that was too fast, but the point is here actually not that you understand the details of this function regression model, but to understand why this is, from a scaling perspective, so tricky. It is so tricky because, well, first of all, you can consider this function here, or this approximation here, actually like a longitudinal linear model, right? You have on the left, like in a longitudinal study, you have participants, you have certain time points, like in a longitudinal study, and then on the right, there's nothing complex anymore, maybe just like a tensor product spline. So it's essentially a gamma model that we have here in the end, and we need to fit this gamma model. But now the tricky part is that we need to fit this gamma model for n functional observations, each measured on q time points. And if you remember from before, n was in the 10,000s, q was in the 100s, so we have already in the millions of observations. So that's one challenge. Well, large number of observations is something that a neural network can naturally handle by using stochastic optimization, right? So you train the neural network, you train your statistical model by using mini batches. You only feed a certain amount of data into your memory at once, and then do this over and over again, and thereby train the model not on all data, but on small batches. So that's straightforward. This is not magic, right? That solves already the many observations. Then we have this tensor product guy here. Why is this so bad? If we take a basis function that is maybe 20-ish, 30-ish columns of large, and the same for this guy, then we are already in the upper hundreds of columns. There's also a trick that is used in statistics to circumvent these chronicle products. It's by using an array formulation. So you can show that this chronicle product can be reformulated as a matrix product, where this gamma matrix is the inverse operator of the vectorization operator. Again, this is something that statistics software also makes available, but it's super simple to implement in a neural network. And essentially, these matrix times matrix multiplications is something that the neural network is optimized for. All right, so that was the second part. Avoid array computations by rearranging the formula, so the chronic product in this case. But then we're still left with these design matrices, and we have these design matrices for all the different predictors and all the different time points. So we need to store a 30-ish or 20-ish large design matrix, this guy and this guy, J times R times. And now if you look at the indices, actually this guy does neither depend on J nor on R, and this only depends on R. So we have basis matrices that are involved in all of these sum terms, but some actually do not depend on the summation indices. And what you can do is, in a neural network, you can simply set these guys up once and tell the neural network in its computational graph, just reuse this matrix. You set it up once, and then you tell the neural network, there is a sum, but you can always use the same object that somewhere in your computational graph is already present. So you don't need to repeatedly set up these basis matrices over and over again, which statistics software does because, it tries to be very generic, and so it has to. So this is called basis recycling. So we avoid setting up large matrices over and over again, by pointing the computational graph of the neural network to objects that we have already set up. So this is not super, like, this is not like magic, right? You could also do this in statistical software, but again, it's super simple to compute in, or to encode in a neural network. And with this, let's check out the results from before, the scalability result, and also here you have some estimation comparison. So that's the ground truth surface, an example ground truth surface. This is the edited model and the boosting software. So you see that these are look very similar. Now I'll include the neural network. You see that the neural network actually is, if you fit this statistical model neural network, it does a very good job. And then if you look at the scaling, well, the scaling is actually constant in memory because of all these tricks that we do. We don't need to worry at all about the memory. So in that way, we were able to solve this large-scale functional regression model problem. And that's solved for now. So now the second part that I was mentioning is this was also challenging. The usage logs, you now know how to solve large, like a tall matrix. We can solve using mini batch optimization. But what about the app usages and the scaling for the number of categories? This doesn't seem to be something that is naturally solved using neural networks. And what you can do there is what we call dynamic feature encoding. So in every statistics software or ML software, at least the ones I know, what you do is if you process categorical data, I can give you an example here. So here are the names of some US presidents. Well, what you do with those in a statistical software, you would encode them in a new matrix using, for example, dummy encoding, right? Maybe you can use a lot of these, the fact that there are a lot of zeros you can maybe use and store this in a very efficient way, but the computational costs will be maybe still of O n times C, where n is the number of observations and C is the number of columns. And now the problem is that C is very large, right? So I have here the ... so it goes far to the right. So what can you do in neural networks? You can instead encode the categorical variable during training by just feeding the names to the neural network, and only during the forward pass you encode the names into this format. So you still encode the names into dummy encoding, but you do this now for a matrix that is of the size B times C. And even if C is in the thousands, you can always decrease B to a number that, well, your memory allows to, right? So in the smartphone study, for example, we trained with batch sizes of 2 or 4 to make this work, and that you can do. But because the optimization is then a bit more tricky, but you can always decrease B if you need like a very wide matrix into your memory. So this essentially, you can do this over and over again for every of these batches, and then avoid in this way the exceeding your memory limits. All right, so and now let's look into what this brings for the scaling comparison. And here are now the approach that we proposed faster. And you can see that with those tricks, we get linear scaling in time and constant memory consumption. So also solved this problem. So to maybe summarize this first part, what I'm advocating is actually not to use neural networks as neural networks, but I'm advocating for using the deep learning software because it's quite flexible, and using stochastic gradient descent optimizers because they allow you to learn things in batches and only require the gradient. All right, so before I move on, are there any questions so far? All right, then the second part of the talk, I will now, well, what I showed you here before, actually, there was something that still didn't work, even though we had this nice bag of tricks. There were just too many app user time combinations in our data, and this result here actually requires an additional ingredient. And this additional ingredient comes from ideas from recommender systems. So I'll first present one ingredient for the smartphone, and then for the smartphone study, and then come to the biomechanics data again. So a quick recap, or maybe a introduction into recommender systems. So what you have in recommender systems, if you use Netflix, if you use Amazon, you have usually users, and you have some products here. In this case, it's whether or not they have, for example, watched a movie. And then maybe we encode yes as 1 and no as -1. And now we try to approximate this matrix. This is a very large matrix. Imagine you have all the Netflix users and all the movies. You want to maybe, well, first of all, you want to store this matrix in an efficient way, but you want to maybe also predict, is this lady here, for example, watching The Dark Knight Rises? Will she likely watch The Dark Knight Rises, right? To make recommendations. And what is done in recommender systems is that you try to approximate this matrix here by learning vectors for the users and learning vectors for the movies. The vectors for the users have the same amount of rows, and the vectors for the movies have the same amount of columns as the original matrix. But if the number of vectors is small, and you still save some memory, you can actually save a lot of memory if this matrix is large. And why does this, well, how do we get then the approximation? Well, we can check out this second lady and The Dark Knight Rises, which use the vector of the lady, which is -1, 0. We multiply this with the vector of The Dark Knight Rises, 1 and 0.9. So -1 times 1, 0 times 0.9 is -1. And this is exactly actually the value we have here if we encode not seeing the movie as -1. And this way we would then do, well, we approximate the matrix not only, but we also can do predictions. All right, so the nice thing is, if you thought, well, this is recommender systems, I'm not really interested in this, I'm a statistician. Actually, recommender systems can well also be understood by linear models. So if you would take this matrix here and put it in a long format, you would get values y for every item, that's the items, and every user. And we want to predict those, and we predict those, and this is a typical, very simple formula of a recommender system, a global mean, that's the average probability that a movie was watched. Then so-called bias term, which is just an intercept for the item. Then we have a bias term for the user, because every user has a certain preference to like how many movies you watch. So this is again just a user intercept. And then comes, this is exactly what you see here on the bottom. V1I are the vectors for every item, and V2U are the vectors for every user. And this was in the beginning of recommender systems, a model that was used in these like databases from Amazon and so on, right? So this was an early recommender system approach. Right, you can do something similar in more dimensions. So you can also factorize tensors. In our case, for example, we had these different study participants over a course of different time points, and behaviors would, for example, be the number, the different apps, right? And in this tensor included are the activities. So if you pick any small cube particle here in this tensor, that would be a combination of who uses which app at which time point. And that's something we want to now approximate. And we could do that by doing the same approach as in the matrix factorization. We could say, let's learn a vector for every person. Let's learn a vector for every app, and let's learn a vector for every time point. If we try to approximate this tensor with like an outer product of these vectors, that would not work well because we would assume independence, right? We would here take a scalar value for some user and say, no matter what app the user is using, this user value has the same value, right? And the same for every time point and every app. So we're essentially saying there's independent dimensions. Like in basic statistics 101 class, when you try to calculate probabilities from their margins, right? You only get that multiplying the margins, you only get the entries in the cells if they're independent. But what we can do is we can use a sum of f of these vectors, and thereby approximate this thing quite well, because at some point, if we increase just f, make f large enough, then we are able to approximate this tensor quite well. So in our case, this was the linear model formulation. What we want is a system that also accounts for time. So these linear systems can actually be time varying, and a time varying recommender system would look like this. We would say we're predicting for every user and every item at a certain time point, we're predicting a value, and now the item bias is a function of the time, the user bias is a function of the time, and this factorization, well, you can use either of these vectors to make time varying. Usually the user vector is chosen time varying. So that would account for our situation with the app user time dimensions. Now we wanted to have this smooth, and so what we did in the paper is to say we approximate this part here in the last part using a basis function approach. So we model the time as a basis function with a basis function, and every of these basis function indices gives a new factorization. So essentially, you're learning a spline, and the coefficients of the spline are a result of a factorization approach. And using this, then we're able to finally accomplish the results that I showed before. So we're able to make this varying coefficient model work and able to scale to these large dimensions. All right, so that was the case. If your data is if you can store this in a matrix or in this tensor, and the things that you want to explain, the y's actually happen to be look like this. You can define the data within some cube, for example. But in the case of the biomechanics data, we have actually input values that live on a certain other domain and output values that live on another domain. So we actually want to do a regression. We don't want to do a factorization. We cannot have like a space that we want to factorize, but these guys live on completely different dimensions and different domains. So we need a regression approach that also allows for factorization to make this application work. And in addition, what biomechanics tells you is that, well, the way you accelerate in one dimension and the way you accelerate in the other dimension, and how you, for example, rotate or something, that all interacts with each other. So we need a lot of these interactions between input features to appropriately model the data generating process. And this is now where the additive factorization machines come into play. So often confused. Before that was factorization, matrix factorization. Now it's factorization machines. I also give you a short intro/recap. Factorization machines were proposed by a German researcher, actually, who was then bought by DeepMind, I think. Was also Professor Stefan Wendle. He had some seminal work in recommender systems in 2010. And the difference of factorization machines and matrix factorization is that we're now in a regression setup, and we want to have all the possible interactions. So there's like an image in the paper, in the original paper, that shows this behavior. So we don't have users and movies and have their combinations of what they watched in some matrix, but now we have another variable. Maybe, I don't know, how much do you want the user to pay for his or her Amazon service? Or I don't know, something else like a coupon. It's how much do they earn? You want to learn something different than just what is included in the user and movie data. But you want to use the user and movie data, and maybe also other data like rated movies, other rated movies, last rated movies, time. You want to use that in your model, and ideally you want to have interactions between all of the features. That's the goal of factorization machines. So what we want to do mathematically is to say, well, our prediction is now an interaction model between every j and every j prime, and j prime go over all the different feature dimensions, and then learn an effect of the combination. That would require you, if we have p features, to estimate p over 2 of those guys, right? So this is again something that scales quadratically, at least in the number of features, and that's also a problem. So what you can do is we can now, instead of factorizing the data, we can factorize the beta. You can say, well, let's not just learn a beta, a joint beta, but let's learn individual gamma variables. So we use the j variable. Whenever j comes up, we use this one gamma, right? We don't learn multiple gammas. We only learn one gamma for j and one gamma for j prime. So this scales linear in p. Problem is that, well, this would assume again independence. If you remember this from before, the tensor factorization, this would not work because we're essentially assuming independence in the dimension here. So what can we do to, well, break this link between j and j prime, which is the cause of this bad scaling, and still do a good approximation? Well, we can do the same as we did before. Instead of learning gamma j and gamma j prime, we learn capital F of those and sum those up. So we approximate this beta by a sum of products, and if capital F is just large, if it's large enough, then we'll actually recover the original beta, or have a good approximation. So back to the study. In this study, we wanted to have these approximations, but the problem is actually these approximations, these interactions should be smooth. So we want to have something that is smooth and interacts. So that was the linear model. And what we actually want to have is something like, we want to model, for example, a GAM model with univariate splines or univariate nonlinear functions in all the j predictors, and then we want to have this guy here in particular. Like we want to have bivariate nonlinear function for every combination of j and j prime. And again, this would scale probably at least quadratic in the number of features. This is very ugly and maybe not so easy to read, so I'll give you some visual hints. So what I'm essentially doing here is I would use a GAM approach for this. I'm now representing, and I'm missing here a sum over j. So here I use just a spline approach, again, by basis function times basis coefficients. And you can do the same for this bivariate term. You can sum over all the j larger j prime, and then you can say, well, every of these bivariate terms can be represented by a sum of, like, a combination of two basis functions in one and the other direction, like in the functional application, times their joint effect beta prime. And again, the problem is here that we have this locking between j and j prime. So we would have to learn p over 2 beta parameters. And well, this is the result if you try to do this. If you try to fit again a BAM, a big additive model in MGCV, you get in this case it's not logarithmic scale. If the number of features increases, you just have the quadratic behavior because you have p over 2 parameters that you need to estimate, and that you can see both in the time and the memory scaling. How can we solve this? So how can we, in particular, make this more cheaper? You can simply make the same approximation as we did before. You can approximate this beta guy here with the locking of j and j prime by approximating it with a sum of individual components. If we look at this formula a bit more closely, we see actually that we can draw this sum to the front, and because these guys are independent, what we can do, we can represent it like this. And why is this so interesting? Well, if we have here basis functions times their coefficient. So if we represent this as a spline, if these are splines, because they're just basis functions times their coefficients, and we call these splines phi, what we see here, what we ended up with is a sum over the product of evaluated splines. So we started with a tensor product spline, which is essentially a combination of the basis times a joint weight that you learn. And we ended up with univert splines that we're fitting, multiple of those, capital F of those, where we just take the product of the spline. This is kind of interesting, right? So we did not combine the basis and then learn a joint coefficient, but we learned individual splines in the unit directions and then combined them with a product. So if you would do that with, and so here are in the rows, in the columns are exemplary coefficient surfaces of some Biward function that we want to estimate. Here's the ground truth. It doesn't look as bright on my laptop as it does here, so sorry about that. You see here, there's a tile pattern, right? And why is there a tile pattern? Because we just used f equals 1 in this case, which essentially says you're learning in this direction of spline, in this direction of spline, just multiply them together independently. This gives you a tile pattern. There's no correlation between those two. But what happens if you now increase f from 1 to 5 or to 15? You see that, and I think you still can see it, although it's a bit brighter than on my laptop. We're essentially having the same estimation performance, almost the same estimation performance as a GAN or the ground truth. So we're actually even sometimes we're even closer to the ground truth than the GAN, which is maybe just luck. There's no property that tells you that you're better than the GAN. But we're doing quite well. You can see this here. So essentially just using 5 latent factors or maybe 15 latent factors, you can get quite good estimation performance. So that seems to work. Now the question is, does it scale better? So we look at this formula from before. And now the nice thing is that we have a representation lemma that says these Biward, if you use this approximation, this Biward function here, the sum over Biward function can be represented like this here. And it's maybe not straightforward to see why this is nice, but if you check out how many times the sum over the predictors comes into play, it's actually only here, and there's no nested sum over predictors and predictors again. So that means essentially you don't have quadratic scaling in the predictors, but just linear scaling in the predictors. And this is exactly what we then concluded from this. You have linear scaling. You scale linear in the number of predictors, linear in the number of bases if you use the same amount of bases, and linear in this latent factor. And your memory costs are actually the memory cost of just setting up for every data point, every observation, every predictor, setting up the matrices. But it's like you would use a unit spline model. It's the same memory costs. Because you do that, right? So here in the formula, you just use the unit splines and just combine them over and over again with here quadratic, and here you take the square over the sum of all of those. And to put it now in perspective, how does this scale? As we were hoping for, almost constant in memory and linear in time. So that can solve the problem if you have nonlinear interactions and you want to have potentially all interactions between all the covariates, and things do not work out in terms of memory or time if you try to exactly compute this. All right, so now just one more extension. What if you want to have a d-order interaction? So something like this here. You have d is maybe 3 or 4 or 5. So you want to have nonlinear interactions in multiple dimensions. So not biword, but triword, and so on. Can we do something similar? You can approximate this using a spline approach with this guy here. This guy, which we call additive higher order term, is pretty ugly. You can see this here. It's a sum over d terms, a product over d, then the sum over the basis function. So you can imagine that this will not scale quite nicely. But what we can show is that we actually have a representation lemma also for this a hot term that tells you that you can recursively represent this a hot term by its previous degree a hot terms. And here the spline again just enters as a unit spline. So D is just an indicator here. It's not a power, meaning that you only need to set up the spline once again in the unit case, meaning that again you get linear scaling. Even if you have D order interaction effects, you get linear scaling in the number of features, and the memory costs actually are the same as in the unit case. Or again, this is quite significant. All right, so how do you final words about these AFM or AFM models? How do you penalize those? Because conventional penalization would not work with, or would not be compatible with this linear scaling. We do some heuristic here. We set degrees of freedom. From this degrees of freedom, you can compute the corresponding penalization using some efficient Demler-Reinsch orthogonalization approach. And that works quite well. The optimization of these guys, as I said in the beginning, you actually don't need a recommender system for this. You can implement this in the neural network software. Although like people in the recommender system literature, they are much better than I am in implementing stuff and are much more into optimization than I am. So what they would do is you can actually show, this is also what we showed in the paper, the optimization problem is actually coordinate-wise convex in these gammas. So you could implement something like a block coordinate descent algorithm. I was maybe too stupid to do that, or my BCD algorithm was way slower than the Adam optimizer in a neural network that worked off the shelf and was much faster. Not saying it's better, much better, just because it turned out to be off the shelf better than what I tried to implement. But all the results that you saw before was based on an Adam implementation. So I just used the default and standard optimizer in neural networks and run these models. Again, just to highlight that it's oftentimes rather straightforward to do stuff in neural networks. All right, so to sum up the factorization part, they can be implemented in neural networks, and if approximation is necessary, then they can provide you with good scaling properties, and that's maybe the remedy if your bag of tricks of neural networks doesn't work in the end. All right, I have now the outlook and the discussion. Are there questions so far, or should I just finish the talk and then we discuss stuff? Yeah? Okay, so it's 5 to 10 minutes. All right. So some challenges in outlook. So I'm promoting heavily to use neural networks, but if we tackle high dimensionality in these neural networks, it still doesn't mean that we can interpret those models, even if they are statistical models, because, well, if you have thousands of predictors, this is not an interpretable model, right? So what you need is sparsity, and sparsity is actually not trivial to get in SGD optimized models. To make this a bit more clear, I have here some collaboration with my PhD student, Chris, who works on sparsity neural networks. And let's consider a very simple setup, the lasso problem. You have like a mean squared error plus an L1 norm penalty. And now both functions are continuous and convex functions, but the second is non-smooth. And an SGD optimizer will not work for a non-smooth problem. It will oscillate, it will not converge to a sparse solution. An SGD optimizer without any proximal step is not made for optimizing this thing here. So that will be a problem if you want to get sparsity in a neural network. You can see this here. So here is the GLMNet R implementation, the state-of-the-art implementation for lasso. Here is lambda, the regularization strength. If you increase this, you can look at the sparsity ratio in your model. It will increase, and at some point, the model will be the null model. If you try to naively implement the L1 penalty in a neural network and try to optimize the gradient descent, you get no sparsity whatsoever. And it's just random fluctuations here. The SGD is not able to make anything sparse, exactly sparse. So what was our solution? Our solution is a so-called Hadamard product parameterization, where you take the beta value and you reparameterize it or over-parameterize it with a Hadamard product U times V, where U and V have the same dimension as beta. And then you replace the L1 penalty by the sum of two L2 penalties. This seems like a very naive approach, like let's just replace penalties. So we're starting with this lasso problem, And then we get the lasso problem where we replace the beta here with the Hadamard product, and here we have replaced our L1 penalty with the sum of L2 penalties. These functions are also actually not the same value, right? So you get in general not the same value between those two functions, but what you can show is their optimal solutions actually coincide. And by over-parameterizing, you induce no additional local minima. So essentially that means if you optimize this guy here and you get a solution, then it's also the optimal solution to this guy. And the nice thing about this guy is it's smooth, right? You traded maybe convexity, but you got smoothness. And smoothness is something that SGD can work with. And so you can run SGD on this problem and obtain the lasso solution. And in our paper, we actually showed a quite much more general result that you can do the same for group lasso penalties. You can do the same for non-convex penalties. You can do this in not just a linear model, but in any neural network at any place in the neural network. So it's a super general result that you can do these optimization transfers. So maybe you have guessed what this, or you can guess what this red part is that is missing. It is actually our approach with the Hadamard product parameterization in L2 penalty. It perfectly recovers the GLMNet solution path. And as I said, it's not restricted to L1 penalties. You can also use a group lasso penalty. Here again, some standard state-of-the-art implementation in R. And we recover that with our approach, whereas if you use it naively, blue one, you don't get any sparsity. All right, so that's a challenge that we solved. Now comes something that we have not solved already if you use neural networks, and that's statistical inference. Probably being a statistician, maybe most of you, then this is something that many are interested in. This is very challenging. Why is it challenging? Well, even if we have a linear model, then we have implicit regularization going on. So because the way we initialize our optimization routine induces biases, the way we optimize with SGD induces regularization. And that, in turn, we would have to account for inference. So this is something my PhD student Rügamer and I recently published a paper on. This is about boosting, but it's also the same optimization routine. What you can see here is a two-dimensional problem. We start here with a zero solution. So we leave out the initialization part. So we start with zero. So there should be no bias from the initialization. But if you look at the optimization path, so this is the red one is if you decrease the penalty of a rich solution, and the others are solutions of gradient descent. And what you see is that these lines cross, so the penalties that you induce by rich and the penalty that you induce by gradient descent, they are at some point, they cross, so they are equivalent, but there's no exact overlap between this arrow, between this red arrow and any of these gradient descent paths, meaning that the regularization that you induce by gradient descent is different from the one that you induce by rich regularization. So there's also a theorem in the paper that says exactly this. So for example, you can show that if you optimize a linear model, then what you get is actually with gradient descent. You optimize it with gradient descent, and you see that we get a mean squared error problem with a quadratic penalty, so a rich type penalty, but this penalization matrix here actually changes with every iteration. So if you would just do one step, you actually would solve a rich type penalization problem, and for that we know how to do inference. But now that the rich type penalty changes in every iteration, and we stop at some point with early stopping, we actually don't know exactly what type of penalization is induced. And that you would have to account for if you want to do statistical inference, right? Because we have some shrinkage going on. We don't know, like we don't get an unbiased estimate, and we would have to account for this in the inference. All right, so there's one, so we have another follow-up work on this, but there's one other solution. You could turn Bayesian. This is work that I do with my PhD student Emmanuel. He's working on Bayesian neural networks and sampling in Bayesian neural networks. So this is a very brief outlook. This is something that was deemed to be expensive in a couple of years ago. Running samplers in such a high dimension is not something that people could imagine is possible. What we did in our recent papers is an improvement over, if some of you know NUTS, the no U-turn sampler. we can actually get much better scaling, maybe not ideally the Bernie Sanders scaling, but it's much better than the previous one. And we're here in the thousands of parameters already. So you can now sample with our software Bayesian neural networks, like large Bayesian neural networks, ResNet type size neural networks, and actually get posterior samples from the neural network. And to the extent that we are now on the same time scaling as optimization routines. So we get those sampling results in roughly the same amount of time as you would get them if you use Adam. And this is something that I think is probably worth also looking into if you're interested in uncertainty quantification of neural networks, or if you just use neural networks for statistical models, you could also use this sampling. All right, so this is already my summary slide. We talked about neural regression models for flexibility and scalability. I was promoting mainly the software and the optimization. I showed you a bag of tricks, and then factorization approaches that allow you to, for example, decompose activities or factorization machines for regression setups, and that these can be adapted for basis function approaches. Thank you very much.